Okay, hello guys, so welcome to my channel. Now in this video, we want to talk about the rational exponent, alright? Okay, so we discussed earlier about indices where we have a particular base and raised to some power. Okay, so this is that exponent we're talking about, the power. Alright, so when we have it to be in its rational form, so we need to know when an exponent has a rational form. So let me just put it down as I'm explaining. So an exponent is of rational form if it is written as a ratio of two integers, right? That is two whole numbers. Let me put it down as n and m, where m is not 0, such that we have n over m. So this right here is a rational form, alright? So we are saying that when we have any number in the power, which is actually a ratio of two integers, that is two whole numbers, alright? Numerator and denominator. So this is an integer and this also is an integer. Now this denominator is not 0, so that we will not have 0 in the denominator, which is not going to be a real number actually. So when we have something of that form, then that is said to be a rational number. All right, just fractions. Example are we have examples. We can have 1 over 4. Okay. You see 1 over 4, 1 is a whole number and 4 is also a whole number. Now it doesn't matter whether they are negative, right? Integers consist of positive and negative whole numbers. So we can have negative 1 over 2. We can talk about 4 over 3. So it does not matter whether it is an improper fraction or not, right? Okay, and so on, provided they are fractions. You can also have, let me say, square root of 16 over 2. So you just have to simplify this, alright? The square root of 16 is actually 4. 4 over 2 is going to be 2. In fact, let me just put it down that 2 is also an irrational number because, 2 is also a rational number, reason being that the denominator here is just 1. Ratio of two integers. 1 is an integer. Okay, great. What if I give you this? Say 0.5 over 2. Is this also a rational number? Remember, we are talking about ratio of two integers. So two whole numbers. This is not a whole number, but this is a whole number. Well, this is also a rational number because 0.5 can be written as a ratio of two integers. 0.5 can be written as, let's say, 5 over 10. Alright? Or you can even put it down as 1 over 2. So let me say 1 over 2 is the same thing as 0.5. So this is 1 over 2 on the top, then divided by this 2 on the denominator. So all in all, we're going to enter with 1 over 4, which is also a ratio of two integers. Okay, very nice, like that, alright? So even if I'm putting them in decimal forms, you can still make them whole numbers, alright? Now, we have some numbers that are not rational anyway. For example, we have the square root of a non-perfect square. Let me take 2. This is an irrational number. It's not rational. We call it irrational. And others like like pi. Pi can be written as a ratio of two integers, alright? The rational approximation for pi is 22 over 7. So 22 over 7 is a rational number, but it is not exactly equal to pi. Pi itself has a value different from that, but though 22 over 7 is very close to it. So pi is an irrational number, and many others, there are infinitely many, right? But that's not really our concern for now. So we are really talking about rational numbers anyway. So let me just go ahead and, okay, so these are the examples of rational numbers. Okay, great. Now, when we have rational exponents, now this is it. Suppose we have a raised to the power of 1 over n, where n is not 1 and n is not 0, Okay, let's just say n is an integer, n is greater than 1. So look at all these. Suppose we have a raised to the power of something. So it is this exponent now, which is now a rational exponent. 1 over something, okay? Now I'm saying that the denominator should not be 1. Alright? You know, we will just be having 1 over 1, which is just 1. That will be a raised to the power 1, which is just a. So there is no point going for rational exponents. It's not a big deal anymore when n is equal to 1. Now I'm also saying that n should not be 0, so that we will not have a raised to the power of 1 over 0, which is going to be a raised to the power infinity, which is increasingly large, provided that a is not negative anyway, or a is greater than 0. Okay, but suppose that this n satisfies all these properties. N is a whole number which is greater than 1. That is, n can be 2, can be 3, 4, 5, and so on. Then it implies that a raised to the power of 1 over n can be written as the nth root of a. Okay, so in one of our videos, when we were talking about the laws of indices, the law number 6 talked about the rational exponent, and I believe you understood. Okay, so if you haven't watched that, it will be necessary to check out the laws of indices, because that is where we build on, alright? That's the kind of foundation on this particular topic. Okay, so this right here is true, that when we have a raised to the power of 1 over n, it is equal to the nth root. Okay, so provided that the exponent, the denominator in the exponent is actually the root. Okay, for example, when we have 8 raised to the power of 1 over 3, the denominator in the exponent is going to act as a root. Okay, so this can be rewritten as cube root. 3 will be here, just like we have n, right? And this will be 8, which is actually the number itself, and this will be raised to power 1. Now this a was being raised to power 1 actually, where the 1 is gotten from the numerator. So assuming we're having, okay, so that is for the example. So assuming we are having a raised to the power of m over n, alright? Now, this right here can be rewritten as, well, let me split the power for you guys to see. This can be rewritten as a raised to the power of 1 over n, we multiply it by m. Well, when we were treating the laws of indices, we saw that when we have a power here and another power out of the bracket, the two of them can be multiplied together. And when we multiply the two powers, we're going to have this, alright? So that is just it. So we know that a raised to the power of 1 over n is equal to the square root of so on. So I will rewrite this as, the expression in this bracket can be written as the nth root of a raised to the power 1, right? Yeah, and we raise it to power m. So that is what we are saying. Alright? That when we have a raised to the power of m over n, it is the same thing as the nth root of a, everybody raised to the power m. Well, this can also be rewritten in another form. We can also see this as, well, I am going to put a raised to the power of, this time I'm going to put the m inside and put the 1 over n outside. Reason being that multiplication is commutative. That is, the order doesn't really matter. Which one do you put first to multiply with the other one? It does not matter, right? Because it's multiplication. Put this one first, here, put this one here. It's the same thing as putting it here and here. Very nice. So this is what I'm actually doing. We see that this is a raised to the power m, okay, in this place, the whole of that. So just like we have here, the whole of that. So we are going to raise it to this. So this is the same thing as the nth root of a raised to power m, alright? So this is still here, just taking the position. Looking at this, you just put it down, the right position. So that is it. So let me remove this just to explain for you. Okay, great, very nice, alright? So that means that this, which is equals to this and this are the same. So whenever we have a raised to the power of some fraction, alright, where the denominator is not 0 and it is not 1, but the denominator, these are just whole numbers. This can be, either you write it as the nth root of a raised to the power m, or you write it as the nth root of a then raised to power m, alright? It does no crime anywhere. So that is very, very nice, like that. Okay, great. So this was a very nice introduction for you, and I hope it is clear enough, all right, based on this. So we will go ahead and look at other things still under the rational exponent. Okay, thanks for watching, and please subscribe to my channel.